problem 13.1, 13.2. Suppose we have a random sample size n from the normal population with the mu and sigma square as the mean and variance. And then we want to do this test. The null hypothesis is the mu equals to mu 0. Alternative hypothesis mu equals to mu 1. Okay, now they are both simple. The mu 1 is greater than mu 0. And then if we ask the probabilities of the type 1 and type 2 errors to be alpha and beta, respectively, then we need to show that the required sample size it needs to be as large. Okay. So now for a random sample of size n, we know that the sample mean, remember we're going to estimate the mu using the sample mean. So the sample mean follows the normal distribution with the mu as the mean and sigma square over n as the variance, right? Because we actually have a random sample from this normal population. So sample mean follows a normal distribution as well, with this as the mean and variance. So under the null hypothesis, the mu equals to mu 0, which will give us this shape. Okay, and under the alternative hypothesis, we have this shape. Mu 1 is greater than mu 0. So if we choose, if we see this, the critical region should be a region such that the sample mean greater than certain number k, right? So the sample mean greater than the k, then we are in the critical region. So here it will be critical region. The other side will be the acceptance region. So now to make sure that the type 1 and type 2 errors have a probabilities alpha and beta, that means so the alpha is the probability that our sample mean falls into the critical region. When the H0 is true, right? The H0 is true means that mu equals to mu 0. So what is the probability that this happens? Okay, so this happens means that X bar is following this distribution, but still it falls into this area. Okay, so that is the we can do a old trick, which is subtract. So for both of these two sides, I'm going to subtract mu 0 and divided by sigma over square root of n, where sigma is known, so it's not an issue. And then assuming that mu is equal to mu 0. So this part here is following the standard normal distribution. So the probability that standard normal distribution greater than or equal to this has the probability equal to alpha means that this thing here should be equal to z alpha. Okay, remember that z alpha is the value. So here, this is the standard normal, 0. This is z alpha. So this is the point such that the tail has an area alpha. The shaded area is alpha. Right? That's the z alpha. And we can look up this value from the table for the normal distribution. Now we have the alpha. The beta can be obtained similarly. The beta is the type 2 error, meaning that when mu is equal to mu 1. So here is mu equal to mu 1. And the X bar falls in the acceptance region, which means that X bar is less than equal to k. So we can again do a same trick, subtract both sides of these guys by mu 1 divided by sigma over square root of n. And then we know that that's just on the left, it becomes a standard normal random variable less than equal to this value is equal to beta, means that so we want to find this part of its negative z beta. Okay, and here this value should be beta because it's just symmetric. The z beta will have another z beta on the right. Okay? It may not be different, may be different from the z alpha. It really depends on what the value of alpha and beta are. But that, anyway, that's the value of this should be equal to z negative z beta. Okay, so now we have two equalities and they share the same k. So I can, by solving both of them in terms of k, and we see that k equals to this, and same time k equals to this. Okay, so this gives us a equality that has this n as an unknown because mu 1, mu 0 they are given, sigma is given, n is given, z alpha z beta can be found from the table depending on the value of alpha beta given in the question. So only the n is unknown, so we just need to solve for n from this equality, and then that's how we get the value as asked about the question.